90 seconds or so, we want to explain what's meant by the polarization of light. We want to explain the law of reflection, which you've now had a little bit of exposure to with the lab we just did. We wanted to distinguish between two allegedly different types of reflection called specular reflection and diffuse reflection. And then we would like to be able to locate images formed by plane mirrors. We might not 100% finish that objective today. Right, so last time we said that the polarization of light meant that the oscillations, right, the transverse electromagnetic waves were all oscillating in similar directions if the light is polarized. And then if it's non-polarized, then we have all different directions of vibration present. Right? So when we looked through the polarizing filters, we found that some sources of light were polarized. In particular, it was sources of reflected light, like the glare off of the desks. And then if we looked at like the overhead lights, like those weren't polarized at all. We saw no dimming, right? But and then you don't see my eye like going away when you're just looking right now, right? Yeah, because the light reflecting off my eye from the overhead lights actually isn't very polarized. So we saw reflected surfaces did a pretty good job at polarizing light. We saw that a second polarizing filter, right, did a pretty good job at polarizing light. And then we also saw like the display screen on the phone did a pretty good job. So anyway, these little filters are able to only allow some directions of vibration to get through. It'll absorb the other ones. All right, so this is just a kind of cartoon of what you saw when we had the two polarizing filters in opposite orientations. So if this was, let's see, which is the first? I guess this is the first polarizing filter. So we have incident on that is all different directions of oscillation. That's why we kind of see some of the crests are kind of pointing up, some of the crests are pointing out towards us. But then this filter is only letting some of those directions through. And if the second filter is rotated like opposite of this one, then none of the light should get through. So we got to see that last time. I believe that modern 3D movies utilize polarization of two different light sources to allow us to see in 3 dimensions. Previously, like in the 80s, maybe even early 90s, we used like blue and red filters to get that same effect. And am I right that there's some like 3D stuff now that you don't need any glasses for? I have no idea how that works. All right, any other questions about polarization of light or our little polarizing filters that we play with? Yeah, Brian.
It's like for the sky. So the light from the sky is only coming from one direction, but the light from the clouds is like scattered in all different directions.
Well, the premise of that one homework question was that the light from the clouds is non-polarized, but the light from the sky is polarized. I did not notice a difference when I looked at the sky and rotated the polarizing filter. I didn't notice a difference, so I don't know that premise is 100% right. I'm sure there's a nugget of truth in there, but I don't notice that.
So is that like why for the desks, like the light's only going in certain directions when it's off the desk?
Yeah, so as it turns out, when light reflects, well, we know that not all of the light reflects, right? So if you look at your desks, if you're not Priyanshi, Jonathan, Maggie, and Kat, like what color is your desktop? Black. And what does that mean? Black means that it's not supposed to be reflecting any visible light, but we can actually see like glare, at least off of some of the desktop. So there must be some light reflecting, and there is a relationship between polarization, direction, and reflection. It's not a relationship that we're actually going to analyze or look at all in this class, but yeah, there is a relationship, and currently in the 12th grade year of IB Physics, that relationship is explored. Not sure if that gets explored in the new version of the IB curriculum that we start next year. All right, so great segue to reflection, because that's what chapter 17 is all about. And you already saw I hope you already saw the basics of reflection in the lab activity that we just did. So when we have light reflect off of any kind of surface, it doesn't have to be a mirror. It reflects in a very predictable way, and mathematically, like as simple a way as we could have, really. So we always draw what we call a normal to the surface when we're analyzing reflection or refraction. And normal, as we said earlier, is synonymous with perpendicular. right? So normal just means we're drawing a line that's perpendicular to the surface that's causing the reflection. And then there are two rays, there are two directions that we care about. We care about the angle, the direction of the incident ray, right? So the incoming light ray, the ray that's going to reflect off of the surface, the mirror, whatever. So we call that direction or that angle the angle of incidence. And then we also care about the angle of reflection, right? So the angle in between the reflected ray and the normal. And we have something called the law of reflection that just says those two angles are equal. Right? We don't have to do any trigonometry, we don't have to do any like multiplying or dividing. Those angles are precisely the same, right? Those always get measured with respect to the normal though. Don't measure stuff with respect to the mirror itself. Were your lab results sort of consistent with that the two angles were similar? Were they identical? Were all three identical for anybody? Raise your hand if they were. I don't believe you. Remeasure. Right? We don't ever get perfect results. So if you're saying that all three of them are perfect, make sure, right? Because you better bet I'm going to get my protractor out and check if I think they're the same or not. All right, so any other questions on this statement that the angle of reflection is always the same as the angle of incidence? Again, this is true if it's a mirror, a desktop, right? Michael's hair, this is true for light reflecting off anything. You've been asking for it. I know. Yeah. So we had a third objective that I said we had allegedly two distinct types of reflection. So what we just looked at on the last slide, what we looked at in the lab at the beginning of the period, we call specular reflection. So specular reflection is the name we have for reflection off of very smooth surfaces. All right? Any mirror is very smooth. Are our desktops smooth, you think? Feels smooth. Mine feels smooth. What about this one? Pretty smooth? Yeah, I think they're probably all pretty smooth. Right? So specular reflection is reflection of light off of smooth things. Right? And that's exactly what we've talked about already. We have our incident light coming in here. We have our angle of incidence labeled A in this diagram. We have our reflected ray, we have our angle of reflection labeled B, right? Specular reflection is what we've already been dealing with throughout today. The other type, called diffuse reflection, is what we get when we reflect light off of rough surfaces. All right? What's an example of a rough surface that most of us have out right now? Paper ends up being pretty rough. Like if we really zoomed in with a magnifying glass, we wouldn't see a nice smooth surface. You might even be able to feel it. Yeah, like the quiz paper doesn't actually, it feels way different than the desk to me. And I can hear it. When I rub my fingers against that paper, I can hear it. I can't hear it when I rub my fingers against my desk. Try it yourself. Yeah, that's like actually somewhat loud when all of you are rubbing against your pieces of paper together. Now there's only like two of you rubbing against your desks, but that doesn't sound too loud. All right, so diffuse reflection is when we're reflecting light off of these rougher surfaces. Now, the law of reflection is still 100% true. The law of reflection is always, always, always true. However, if we look kind of microscopically at our piece of paper or at a rough surface, right? If we want to draw a normal at different places, those normals are not all going to be parallel, right? So here, this could be our piece of paper, like on a very zoomed in scale, and we have ignore the blue and red. We're not changing blue light into red light. We're just showing blue and red to illustrate the incident rays and the reflected rays. So we have these. Oh, how many incident rays of light do we have? Yeah, I think it's 5, right? They're labeled A, B, C, D, E. We have 5 incoming rays of light. They're all parallel. Right? That's not so weird. So it's the same light source that is shining on our piece of paper. So we have 5 parallel incoming rays of light. If I draw a normal at each spot where the incident ray hits, it has to be perpendicular to our reflecting surface at that spot. So this one points pretty much straight up, not exactly. This one points all the way to the left. This one points a little bit to the right. This one points a little bit less to the right. This one points quite a bit to the right. So we have normals that aren't in the same direction, but the law of reflection is still valid. So this reflected ray should equal that incident ray. This reflected ray should be the same as that incident ray, right? The law of reflection is still 100% valid, but our normals are not pointing in the same direction everywhere. All right, so it's not really a different type of reflection. We always have the reflected ray, the angle of reflection equal to the angle of incidence, but it kind of yields some different properties of that reflected light. So here's another view, right, where this time they're using like green for the incident rays and cyan for the reflected rays. We do have, I think, 6 incident rays this time. And then if we look at the reflected rays, some of them are kind of going off to the right, some of them are going to the left. So with rough surfaces, we don't have all of the light appearing to be reflecting parallel. Follow-up questions about the law of reflection still being valid when we're reflecting off of our paper or other rough surfaces. Okay. Did anybody drive or ride in a car like last night, like after it was dark? I didn't. Ben, you did? Were you driving or just riding?
Driving.
Driving, okay. Is it supposed to rain all day today? I'm not sure. No, I think well, my barometer is telling me that something's going to change today. I'm not sure. But if you are driving tonight, like after dark, I want you to pay attention to if you can see your headlights in the road. So I don't think you'll be able to if it's raining. Is the road surface rough or smooth? Very rough. Anybody ever tried to like skateboard or rollerblade on the street? What's it feel like? I hate it. I hate it. It like makes like my spine vibrate in it. I don't like that feeling. Sidewalks are fine, but on the actual asphalt, I don't like skateboarding on that. Very rough. Very rough. And that's a good thing for a whole number of reasons. Right? It's a good thing for like frictional reasons, right? And you can come to a stop more easily on a rough surface, a larger coefficient of friction. But it's also really good for like seeing purposes. All right, so it's nighttime. Where are these incident rays coming from? Your headlights, right? So here's your car, right? Here's Ben, right, driving, and his headlights. Your headlights are angled down quite a bit. You can change that, right? Like how do you change that? Yeah, it's called like your high beams, right? So if you turn the high beams on to see further down the road, all you're doing is changing the angle of the headlights a little bit. But normally they're pointing pretty much down, right?
It's illegal to use high beams.
What do you mean it's illegal to use high beams?
Unless it's a rural area.
It's illegal. Like you get a ticket.
Yeah.
No.
That's. I mean, it's been 20 years or more since I took driver's ed. It's rude. It's very rude to use your high beams if there's other cars around. What?
It blinds other people.
It sure does.
If there's nobody in
It's
front
not
of you, you're allowed
illegal.
to use it. You're supposed
Yeah,
to use it.
I don't know that it's illegal. I don't know that you could get a ticket. But if you're a jerk if you're using your high beams when there's other cars in front of you or heading towards you. Even if they're going in the same direction as you in front of you, you don't use them. Well, whatever. We're not using high beams, so it doesn't matter. We're using the regular ones. Now, some of these rays of light that we're sending from our headlights, they reflect in all different directions because the road is bumpy. So if it looks like we have 6 of them, all right, so one of them's reflecting really far in front of us, this one's reflecting pretty far in front of us, these ones are reflecting pretty far in front of us, this one's reflecting back towards us. I don't even know what happened to the 6th one. We're only going to be able to see the road if any of these reflect back towards us, right? Ben's right here. He's only going to see light that reflects towards his eyeballs, right? And that's going to be relatively few of these reflected rays of light. It's going to be some, because the road is rough, but he should be able to see the street illuminated, because some of those rays will reflect back to him. Questions about that? Questions about on the asphalt, because it's rough, some of the light will reflect back to him and he'll be able to see the road because of that. Yeah?
Would it be better on a smooth surface?
No, it'd be terrible on a smooth surface. Right? If you can pretend like driving on a mirror, none of the light is going to reflect back to you. It's all going to reflect forwards. right? You won't see any of it. That would be bad, right? And that's what happens if it's raining like a lot. Because when it's raining a lot, right, all these little like pits in the asphalt get filled in with water, right? And light can reflect off of water. Some of it refracts into the water. But most of it, a lot of it will, especially at small angles, will reflect off of the water. So if we have all those little like nooks, crannies, whatever, submerged, and we have a very flat surface of water, then we're going to go from diffuse reflection with the rough surface to specular reflection with the smooth surface. And how many of those 6 rays is Ben going to see now? I think I lost one again. None, right? And he won't even be able to tell that his headlights are on. Now, normally, unlike most roads around here, there's like street lights. So he will be able to see the road surface, because even though he's not going to see any of the light from his headlights, right, there'll be a street light here, which is giving off light, and some of that light will reflect to Ben. But like on my road, I don't know about any of you, I live like on kind of like a rural road, there's no street lights, right? So if I'm driving at night and all the nooks and crannies are filled in with water, I cannot tell that my headlights are on. There'll be a little bit of light because like the moon's out, maybe people's like yard lights are on, but very, very hard to tell that your headlights are on at night if it's raining a lot. So if you're driving tonight and it's still raining, like check it out. And I meant to take pictures over the weekend. I even brought my camera home, but Michael.
Would like other cars be able to see well since it's reflecting off?
Sure, so if there's other cars coming this way, yeah, Ben's going to be able to see light reflecting towards him from their headlights. Or if there's cars in front of you that have their brake lights on, yeah, you'll be able to, I mean, it would look red, it might be pretty. But we will need some other light source besides your headlights if you want the road to be illuminated. And it's not going to be pitch black, because a little bit of the light does refract through, but you're really not going to be able to tell that your headlights are on. Alright, so what the heck am I saying here? I'm saying here that driving at night, right, if the road's nice and dry, you're going to be able to see the road in front of you, no problem if your headlights are on. If the road is wet, right, you might as well just turn your headlights off, because none of that light's going to get back. Don't turn the headlights off, that is illegal. But if you flick them off real quick, like you probably wouldn't notice a difference in the road in front of you being illuminated. Alright, other questions about the diffuse reflection off of rough surfaces and the specular reflection off of smooth surfaces? Okay. Law of reflection, valid for both. Alright, let's do a couple of quick questions to make sure that you're with me so far. So let's have a ray of our favorite cyan light hitting a mirror at an angle of 25 degrees to the normal, right? Don't discuss this with your neighbors or your foursomes. What angle does the reflected ray make with the normal? Oh, did I have, I may have had, no, I guess I didn't make this multiple choice. All right, what is it? We're not sure? Some of you are sure. So let's draw it, right? We're supposed to draw pictures anyway. So here's the mirror. Here's the normal. We have to draw the normal on there. I don't have cyan, but I have light blue, close enough. So we have our incident ray. Ugh. All right, well, we can do regular blue. Uh-oh. Regular blue, okay, 25 degrees with respect to the normal. And then the reflected ray, if it's following the law of reflection, which it has to, then that's going to be 25 degrees also. So 25 degrees should be the answer here. All right, let's do one more while I retrieve the marker. All right, this time ultraviolet light, so we actually won't be able to see it with our eyes. 40 degrees with the desk. What's the angle of reflection there? Take 10 more seconds. All right, what's the answer here?
40.
What?
40 degrees.
I think I'm hearing 40s. Oh, I don't like that. I don't like 40. All right, here's the desk, right? Normal. The UV light hits the desk at an angle of 40 degrees with the desk. All right, so 40 degrees is here. This is the desk. So the angle of incidence is always the angle with respect to the normal. That's 50 degrees here. The angle of reflection is the same as the angle of incidence. So the angle of reflection is 50 degrees. This angle down here is 40, but we don't care about that, right? The angle of reflection is always with respect to the normal. don't get tricked. Don't get tricked. And you'll have some homework questions, with this phrasing also. But 50 degrees. You say 40, that's wrong. All right, so other questions with the UV light. All right, fantastic. So let me turn this, no, let's do one more question. Sorry, indecisive. I have some mirrors up here. You might need to move your head down a little bit to be able to see classmates, but I'd like you to see who you can see. Is there anybody that can't see anybody? Great. Without like screaming or shouting, can you just kind of check with some of the people that you can see and ask if they can see you also?
Yo, Will.
Hurrah.
Yeah, I can see you, Rich.
Jack.
What's up?
I will.
Tom's way back
Hey,
there. in the back.
Janelle.
I see you, girl. Maybe a little bit Janelle if I move over. Hi, Janelle.
Hi, Rachel.
Now, Janelle, if you do see him, not if you want to see him.
Ouch. Breaking self-esteem.
All right, so most of you have checked. So did anybody find that you could see somebody but they couldn't see you?
You can see the shoulder of Janelle. Janelle, can you see me at all?
Yeah, I can see that.
All right, so nobody found someone that you can see them but they can't see you. All right, so that should kind of always be the case because of this law of reflection, right? So if light from the overhead lights is hitting Rachel and reflecting towards the board, right, it's going to reflect so that the angle of reflection equals the angle of incidence. So if Jenna can see her, then Rachel could also see Jenna from light that hit Jenna reflected off the mirror, reflected to her. So it should 100% be the case that if somebody can see you, you can see them also, and vice versa. All right. So I have another question. This one was multiple choice, and this one I will ask for you to talk about in your foursomes. So let's do simple numbers, right? You're 6 feet tall, like exactly. What is the minimum height of a mirror, a wall mirror hanging on the wall, that you would need in order for you to be able to see your entire body, like from head to toe? All right? And I have 5 different choices here. So in your foursomes, could you please talk about this and hopefully reach some sort of consensus on what your favorite answer is?
I want to see how it looks like. Oh, it actually not better. What do you think?
Alright, so what's the any size mirror? Because if you move that one on the mirror, it's
I don't think it matters. So you can be anywhere you'd like that you think would give you the smallest mirror. All right, they look done, you look done, you look done. These two groups might need a little more time. Looks like 4 of the 5 of you are done. Let's go 5 more seconds. All right, so let's see. So Brian, what did your group go with?
You said any size mirror?
Any size, you should D. All right, let me record these. One vote for that. Jenna, what did your group say?
D.
E?
D.
D. All right. And Kat, what did your group say? Which one? D again. All right. And Janelle, what did your group say? D. All right. And Amanda. Everybody went with D. Any size mirror will work. All right. I don't think so. I don't think so. So I took one of the mirrors off. Let me. I guess I'll put it on the wall. Well, is it better if it's high or low? Were you gonna have a better chance of seeing your whole self? If it's high or low?
Higher.
Higher?
Medium. I don't know.
In the middle? So is it like this? This?
Higher
Tilt it?
up, it's a
All right, come on, Magna, get up here. Come on.
Come on, Meg.
Let's just do it
knows
over
how to
here
place
so
mirrors.
Sharita will be able to see also. Alright, so I'll do whatever you want. You can stand wherever you want. Alright, so you tell me, let me just fold these so I can move it. You tell me higher, lower, tilt, whatever. I'll do whatever you ask me to do. Wherever you want to stand. I mean, not on the table, but like wherever else. Alright, so if she started up close, now it looks like she's going like far away. Now she's going further away.
You have to tilt it forward.
Tilt it.
No.
Like this. She's going even further away. Alright, so at that position, all the way in the back of the room, can you just kind of tell us what can you see right now? What's the highest you can see, what's the lowest you can see? You can see half your body. So you can see the top of your head to like your waist. Okay. Alright, so it didn't work. Or at least this size mirror didn't work. Right? So apparently, at least if you're Meghna, it doesn't work. Now she's not 6 feet tall, but I don't think that really matters. I think B is the best answer. I think B is the best answer. And Meghna actually said she could see about half of herself. 2 of these would be about half of her height. So let's look at why. Let's look at why. All we need to look at this is knowledge of the law of reflection, right? So here's Meghna, right? And here's, well, the mirror could be a full-length mirror, right? But that's overkill. We don't need all that. All right. So if Meghna's going to see her toes, right? She needs light from her toes to be heading towards the mirror, hit the mirror, and reflect to her pupil, right, to her eyeball, right? So assuming her toes are directly underneath her eyeball, right, that light would have to hit the mirror like exactly halfway between the toes and the eyes, right? So it should be exactly halfway, and that has to abide by the law of reflection. So this angle of incidence has to equal that angle of reflection. So Meghna looks at this spot on the mirror right here, and that's where she sees her toes. Follow-up questions about, she looks here and sees the image of her toes. Okay. So she wants to see the top of her head also. So she needs to look, again, if the top of her head is right above her eyes, then she needs to look exactly like vertically, midway between her eyes and the top of her head, right? Because if light from the top of her head is coming towards the mirror, it has to abide by the law of reflection. So, I mean, it's such a small angle, I really can't draw it. The angle of incidence has to equal the angle of reflection also. So if she looks right here, she ought to see the top of her head. So all she needs is like a height of mirror equivalent to like half her height. In fact, a tiny bit less. It would be half of her height if her eye was like up here. Are there animals like that their eye is up here? Frog are kind of like that. All right, so if we're talking about a frog, it'd be exactly half their height. If we're talking about a human, it's very slightly less than half our height. All right, so if you're 6 feet tall, 3 feet of mirror is plenty. But you need at least that much. If you're close, if you're far away, doesn't matter, right? You need 3 feet of mirror. Follow-up questions about that. Okay, now we're smart, right? We wouldn't be here if we weren't smart. No, more than relatively. Way more than relatively, right? So we don't often get tricked, particularly by plane mirrors, about where things are located. But if we can force ourselves to be stupid for a minute, Meghna is looking here and she's seeing her toes. She's also seeing the floor. She's also seeing the floor when she looks here. In reality, it appears as if her toes are back here behind the mirror, right? Because she's looking here and seeing her toes, but we know that our toes are on the floor. So really, it appears as if her toes are all the way back here. And it appears as if her head is all the way back here, right? Because she's seeing this thing, but that light is coming from this direction. So it's looking like that stuff is located behind the mirror. Because it appears to us, if we can get rid of our smarts for a minute and our 15, 16 years of experience of using mirrors, it appears as if Meghna herself is back behind the mirror. So because it looks like the